Complementary to the question of asking how many successes did we have in a certain number of trials is the question, how many trials are we going to perform before we get a success? So the idea is we perform independent trials. Let's say the ith trial is xi, the outcome. And this is 1 with probability p, 0 with probability 1 minus p. So we have a success and a failure. Those are the only two things that could happen on the trial. This is a Bernoulli trial. Let's let x be the number of trials until the first success. Including that successful trial. So if x is what we're measuring, the number of trials to the first success, we write x as a geometric random variable with parameter p. I claim that the probability that x equals k is 1 minus p to the k minus 1 p. And the reason is we have 1 minus p is the probability of failure. So the first k minus 1 trials fail, and then p, the kth trial, succeeds. We don't need any n choose k because we know exactly the orders these are going to happen in. All of the failures first, and then we stop after the first success. So, for example, let's say we roll 2 dice until getting 7. The probability that we'll get 7 on any roll is the number of ways to roll 7 over the number of ways to roll 2 dice, 36. And that is, let's see, we could get 1 and 6, or 2 and 5, or 3 and 4, 4 and 3, 5 and 2, 6 and 1, over 36. So that's 6 options over 36, so 1 over 6 is the probability of success here. Oh, sorry, that's the probability of success. And then if we want to know the probability it takes k trials to get that success, so let's say the probability that it takes 5 rolls to get our first 7 is, so we fail 4 times, and then we succeed on that last trial. So 5 to the 4th over 6 to the 5th. Alright, so let's add up these probabilities and make sure they add up to 1. Now to check that the probabilities sum to 1, And to compute expected value of x and variance of x, we need some summation formulas. So these are formulas that you've seen in calculus. So if we add up all the powers of r from the 0th power going to infinity, maybe I'll write this in summation notation also. That's 1 over 1 minus r. And then another series we'll need the sum of is 1 plus 2r plus 3r squared plus 4r cubed, etc. So this is the sum of, let's say, I to the r minus I. Sorry, to the r I minus 1. So the exponent is 1 less than the coefficient. I guess we can sum this from 0 to infinity or 1 to infinity. Same. No, this one we need to decide. I'm going to write 0 to infinity, although the 0th term would be 0 times something, so it doesn't show up. And this is 1 over 1 minus r, the quantity squared. Alright, so using these, let's look at the sum of the probabilities. So if we add up the probability that it takes, I guess we can't have 0 trials. We can have 1 trial is the lowest number of trials we can take to get a success. So that is, so we succeed the first time, fail and then succeed, fail twice and then succeed, fail 3 times and then succeed. So this looks like a sum of powers of 1 minus p, except that we have a factor of p everywhere. So we can factor that out. So this is p times 1 plus 1 minus p plus 1 minus p squared plus 1 minus p cubed, etc. Which is p times, this sums to 1 over 1 minus whatever we're adding powers of, so 1 over 1 minus p, which is p times 1 minus 1 is 0, minus negative p is plus p, so this is 1 over p. So the sums to 1, which is good, because the probabilities should sum to 1. Now let's look at the expected value of y. Sorry, the expected value of x. So it's basically the same sum, except we're going to put a 1, a 2, a 3, a 4 with all the probabilities. So 1 times the probability of, so we want I times the probability of x equaling I. So 1 times p plus 2 times p, 1 minus p, plus 3 times 1 minus p squared p, 2 failures and a success, plus 4 times 3 failures and a success. Now what does this look like? Again, I guess we have p everywhere that we can factor out. P, so this is 1 plus 2 times 1 minus p plus 3 times 1 minus p squared plus 4 times 1 minus p cubed, etc. And that's exactly this summation here. So the sum in the parentheses is equal to 1 over 1 minus p, that whole thing squared, which is p times 1 over, we said that what's inside here is p, so p over p squared, which is 1 over p. The expected value of x is 1 over p. So that means in the example where we're waiting until a roll of 7, we expect to wait for 6 trials because the probability of success is 1 over 6. All right, now let's compute the variance. Variance of x is expected value of x squared minus expected value of x, the quantity squared. Which is expected value of x squared. We just figured out what expected value of x is. It's 1 over p. So minus 1 over p squared. Now the expected value of x squared is a little bit tricky to get. There's one way in the book, and I thought of another way to do it. Neither way is absolutely beautiful, but let's look at both. I claim that the expected value of x squared is 2 minus p over p squared. So first proof, let's keep these summations here in case we need them. So the expected value of x squared by definition is 1 squared times p plus 2 squared failure success plus 3 squared 2 failures and a success plus 4 squared 3 failures and a success, etc. So we've got a p in every single term here. So this is, we factor out the p, 1 squared plus 2 squared, 1 minus p, plus 3 squared, 1 minus p squared, plus 4 squared, 1 minus p cubed, etc. Alright, so what's inside the parentheses here is a series whose sum we probably don't have memorized. It's not one of these two. But it turns out that if we sum n squared r to the n, as n goes from 0 to infinity, that equals r times 1 plus r over 1 minus r cubed. So this is something that we could look up, but we don't have memorized. So for that reason, I think this proof is a little bit imperfect because it uses a fact that we couldn't find easily, well, unless we look it up on the internet or something. So we have something that looks a little bit like this. Numbers squared times r to that number. Actually, we've got number squared times r to 1 smaller than the number that's squared. We have 1 minus p to the first here next to 2 squared, 1 minus p squared here next to 3, 1 minus p cubed next to 4. So let's multiply by 1 minus p and divide by 1 minus p, so that we get something that has this form, so that we can use that formula. So I'm going to divide by 1 minus p on the outside and multiply by 1 minus p on the inside, so that the power of 1 minus p matches the number next to it, which is squared. And then we have p times 1 minus p, and now this is exactly the form of this formula. 1 minus p is the r that's getting raised to different powers. So I guess we have 1 minus p and 2 minus p over 1 minus p, that whole thing cubed. Now right away I see I can cancel a 1 minus p and a 1 minus p. So we've got p times 2 minus p over 1 minus p we said is p. 1 minus 1 is 0 plus p, so that's p cubed. And now 1p cancels from the numerator and denominator, and we've got 2 minus p over p squared. So that's what we claimed. So it's sort of a short proof, but it depends on knowing this formula here. So let's do a different proof that doesn't depend on knowing this formula. Although this different proof depends on knowing a trick that you might not think of if left to your own devices. Okay, so we could start by writing this expected value again and then maybe not recognize the sum because we don't know this formula. But we claim that the expected value of x squared equals q times the expected value of x squared plus 2q expected value of x plus 1. So to see this, we'll write the sum in summation notation, and let's let q be, okay, I put it in the claim, so I should say where q equals 1 minus p. So to see this, we'll write expected value of x squared equals a sum of, let's see, something times q to a power times p. So if we have I squared, then the power of q is going to be 1 less than that, I minus 1. So we have a sum of I squared q minus 1p as I goes from, I guess we could do 0 to infinity or 1 to infinity. It doesn't matter because the 0th term would be 0. Let's do 1 to infinity, and then let's do the changing index trick, where if we reduce this number by 1, then we have to increase all the i's to I plus 1's in the sum. So then we have I plus 1 squared q to the I p. Now I plus 1 squared is I squared plus 2I plus 1 q to the IP. And now we can write this as 3 different sums. Sums of q to the IP times I squared times 2I and just a sum of q to the IP. So I squared q to the IP is one sum, plus 2 I q to the IP plus the sum of q to the IP. Alright, hopefully this equals q times expected value of x squared plus 2q expected value of x plus 1. So the first term actually looks a lot like expected value of x squared. It's got an extra q in it though. We would want a q to the I minus 1 next to the I squared rather than a q to the I. So if we pull a q out, then that is q times expected value of x squared. Now the next term looks a little bit like expected value of x. I times probability of I. But actually the probability that x equals I would be q to the I minus 1 times p, not q to the I times p. So let's pull a q out of that. So we have 2q expected value of x. And then if we look at this last term, so 0 failures and a success, 1 failure and a success, 2 failures and a success is actually the sum of all the probabilities of the geometric distribution, which we just added up and verified equal to 1. So indeed, expected value of x squared does satisfy this equation. So that means we can solve for expected value of x squared in terms of the other things. So let's see, if we collect the expected value of x squareds on the left-hand side, we've got 1 minus q of them. And then on the right-hand side, we have 2q, expected value of x, which we know is 1 over p, plus 1. And that means expected value of x squared, 1 minus q is p because q is 1 minus p. So we divide both sides by p to get 2q over p squared plus 1 over p is the same as p over p squared. So that's 2 times 1 minus p plus p over p squared. 2 minus 2p plus p is 2, minus 2p plus p is minus p over p squared. So indeed we get exactly what we claimed. And then I guess I can make a new claim about the variance, or we can just compute it. Variance of x is expected value of x squared, 2 minus p over p squared minus expected value of x, the quantity squared, 1 over p squared. So 2 minus 1 is 1, 1 minus p over p squared. So in the rolling dice until we get a 7 example, we expect to need 6 trials because 6 is 1 over 1/6. And how much our experiences can actually vary from that expected value. So we have the variance of x being 1 minus 1/6 over 1/36, which is 5/6 over 1/36. I guess I could write this as 5 times 6 over 36. 30/36 over 1/36. So I guess that's 30. The end.